The previous theorem gave the distribution of x bar, so the sample average, when the population is normally distributed. But what if the population is not normal? What if we're measuring leakage current for transistors, for example? What if it's not normal, or what if we don't know? We're not sure. Bolts, diameter of bolts, okay, normal distribution, but if we don't know, what can we do? And the essential limit theorem here will give us the answer. So, the essential limit theorem says, let a population have any distribution with a finite mean mu and a finite variance of sigma squared. Then, the essential limit theorem says, no matter what the population distribution is, the sample averages, the samples taken from that population, samples of size n, will be normally distributed if the sample size is large enough. And as we said before, with mean of mu, and with variance of sigma squared from the population over n. And it's known that even small samples of 4 or 5 will work for this if the original distribution of x is not too non-normal. So this is the reason. This is important because any statistical methods that we are going to apply in this course, any methods that are based on x bar, based on the sample average, are known to be robust with respect to the normality assumption for the population. So in other words, if a method is based on the sample mean, then even if we need to assume normality for the population, the conclusions from our method based on the sample average will remain valid, even if the normality of the population is not quite true. And we'll be seeing this in Session 4 and Session 5, confidence intervals and hypotheses testing about the population means and variances. That's in Session 5. And we'll be using this in Session 4 for the control charts. And we will know that we can use those methods and that they will be robust because of this very important essential limit theorem. I hope that's clear. I just would like to show you the picture. I wanted to draw this, but this pen is difficult to use. So if we have a distribution of our random variable x, so here I do have a normal distribution, bell-shaped. We've got it centered about a mean. We've got a standard deviation of sigma. Now, if we take, so this is the population, tabletops, x bar, distributed with mean and variance sigma squared. If we take a sample from our population, again, oh sorry, this is x. Ooh. Okay. If we take a sample from our population, of size n, this will be normally distributed as long as n is bigger than 4 or 5, big enough. Mean and variance of sigma squared over n, where n is the sample size. And here we see a picture of x bar, f of x, also centered around mu, with variance of sigma squared over n, or standard deviation of the sample, equal to the population standard deviation divided by the square root of n. And what's important with this picture? What do you notice about these two pictures? Of course, you see that this top one is wider. It's fatter. It has a greater variability. And we know that the standard deviation is a measure of this variability, and that's something we're interested in, the quality. Here we have a thinner population. And that's because when we apply the essential limit theorem, our variation of the sample is smaller than the variation of the population. And this is probably obvious to everybody. And the average values don't contain the extremely high or extremely low values that the individual values take. So although the mean value remains the same, the variability of the data when we look at the sample average is less. No? So let's do one last example here. We have samples of size 4, so n equals 4, are taken from a population whose distribution is not known. We don't know. But the mean and the variance are known. Now, what we're interested here, this is to lead us into session 4. We're interested in setting limits for x bar. We're interested in setting limits for our sample mean to include 99.73 of the x bar values. So I'll come back to that in a minute. First of all, as we know from the essential limit theorem, even if x is not normally distributed, the sample average from a sample drawn from this population x will be normally distributed. So if we know that x is normally distributed with a mean of 2 and a variance of 0.0225, so we know that, we can use our essential limit theorem, and we know that the sample average, in this case for a sample size of 4, is also going to be normally distributed with a mean of 2 and a sigma squared of the sample equal to the population sigma squared over n. And if we calculate that out, again, the mean of the sample averages is 2, and then the sigma, the standard deviation of the sample average will be 0.075. Now, our question. We are interested, let me go back one, wait. Let me draw this here. This time I will try to draw it. This is our sample average, centered about a mean of 2.0 with a standard deviation of 0.075, sample standard deviation. This is our distribution function of our sample average. Now the question is, we want to set limits for the x bar to include 99.73 of the values. So we want to have a limit here and a limit here. And what we're looking for (99.73) of our sample averages, 99.73% of our sample averages should be contained within these two limits. So what that means is, out here, we have only very small 0.135% of our data will be below the lower control limit, or below the lower limit, we can put lower limit, and here we have the upper limit. So how do we get that? We look at our z-table, and we see for this value we get a z equals 3. So this means that in order to include 99.73 of the x bar values within two limits, these limits must be located at a z equals 3. That's a 3 sigma difference. 3 sigma difference. Can you read this? Can you read this from the mean? Well, we know what sigma is, right? 0.075. So we can just simply calculate them. The limits must be at the mean plus or minus 3 sigma, where these are the mean and the sigma for the sample average. And so we get the values, can't quite read this, you get the lower limit at 1.775 and the upper limit at 2.225. So again, if you take samples of your population and you calculate the sample average, every day you calculate the sample average, 99.73% of the time, your sample average will lie between these two limits. Just a very, very small amount of time, you will have a value that's higher or lower than those limits.